Hello everyone, today we're going to look at usaco-training the castle. In this problem we're given basically a n by m grid, which basically two adjacent cells are either connected or not through a wall. So for this example you can see that between 1, 1 and 2, 1 there is a wall. And for example, in between 1, 2 and 2, 2 there is not a wall. And then we're supposed to find, here we go. So we're supposed to find 1, the number of rooms the castle has. And for example, over here, you can see that this region is a connected component. This region is another connected component. Here's another one, and another one. So that would be basically the count. And then we're supposed to find the size of the largest room. And then basically the size would just be you just loop through each of those components and just take the maximum size. Okay, and then we're supposed to also find the size of the largest room that can be created by removing one wall. So you could just choose to remove any wall, and then you would just merge these two components. Okay, and we're also supposed to find the single wall, or the wall that was used to make the largest room possible. Okay, so we're given some numbers over here. And then it tells us that the mapping is basically over here. So for example, 11 would be equal to 1 plus 2 plus 8. So then that means that for cell 1, 1, there would be one wall to the west, one wall to the north, and one wall to the south. One wall to the west, one wall to the north, and one wall to the south. Basically, and then here it is. For example, you can take 13, for example. 13 is equal to 8 plus 4 plus 1. So that means that there would be a wall to the south, wall to the east, and a wall to the west. Okay. And then we're also supposed to choose the optimal wall, which means that we're supposed to first find basically the most west one, and then if it's tied, then we choose the most south one. And then we choose northeast before east. And yeah, that's it. So let's actually draw out the problem. I'm just going to, okay. Let's use black. Okay, so we have 4 by 7 grid. So 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7. Okay. So I'll just use a blue edge to mean that there is a wall in between. So as you can see, all the outer has wall. Okay, so just looking at the diagram, there's a wall here. There's also a wall here, 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 here. Okay, and over here we have 2, 1. There's also one here, and I think that's it. Oh no, there's also a wall over here. Okay, so that's basically so here are the all possible walls. So I'll actually just mark these with with like which rooms they're in. So as you can see, basically let's call this ID1. So this is 1, 1, 1, 1, 1. Since they all belong in the same room. And let's use another color for 2. So we have 2, 2, 2. Let's use yet another color for 3. So we have 3, 3, 3, 3, 3, 3, and 3. Okay, let's use another color. 4, 4, 4, 4, 4, 4, and 4. Let's just use black for this one. So we have 5. So we know that the total number of rooms is 5. So basically number of rooms equals to 5. And then basically to find this, we can start from any point. Let's just say we can start from this point. And then we just basically traverse the graph and we just go down if there is no wall down. And we can just mark this component as visited. And we can do it for each of these nodes. And then now we need to find the size of the largest room. And we can actually just, because for each of our components, we can find out the size, but by counting the number of like rooms it has, or the number of cells it has. For this example, you can see that component number one has 1, 2, 3, 4, 5, 6, 7, 8, 9 rooms, or 9 cells. And let's just say component number 3 has 1, 2, 3, 4, 5, 6, 7 cells. And basically, you just take the maximum among all the like size of the components. Okay, so now you know how to find the number of rooms, and you know how to find the maximum room size. Okay, so now you need to find the maximum room size by removing one wall. So for example, if you try to remove, let's just say if you're removing this, actually there is no wall there, so, or if you're removing, let's say, if you want to remove this wall, then it wouldn't make a difference because this thing, or this cell and this cell is already in the same component. So then, you can try removing another wall. For example, you can see that if you remove this wall, which, as you can see, the left side, or one of these sides, belongs to component number 1, and the other side has component number 2. So if these are different, then you know that by removing this wall, the resulting size would be the size of this component, and then also the size of the other component. Okay. So now we just need to basically simulate removing every possible wall. Okay. Now basically to find, so now we need to, now we know how to find the largest room by removing a wall. Okay, so now we need to find which wall to remove. Okay, so we're given some constraints where we're supposed to move. The wall should be as west as possible, and then it should be as south as possible. And then we should always choose north before E, or north before east. So as you can see, by removing this wall, this would be like the optimal solution, because the answer would be 9 plus 7, which is 16, which is what we want, because that's the like largest size. And then for this, our answer would be, since this is 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7. This would be 4, 1, so the answer would be 4, 1, and this would be east, so east. Okay, so that's basically it. And also, this problem is basically a flood fill problem. Okay, so here we go. Let's include our bits. Okay, so basically, we're given n and m. So you can read n and m. And then let's actually have like a structure representing, namespace, our like cell. So let's call this cell. So our cell should basically store if there is a wall from like to north to south to east and to west. So let's actually first have like a direction. So let's call this char direction. It will be equal to, let's just say, north, south, or northeast, south, west. Okay, so we need to have our cell. So to do this, actually, I think there's an error. Okay. Okay, so we need our direct, like if there's a wall. So let's call this a vector, a boolean, and there should always be a size for it. Let's call this w wall. So this should store, let's just say, w of 1 should store if there is a wall to north, and vice versa. Okay, and basically, I guess that's it. What we need for now. So now we need our cell. Let's call this our grid, and there should be size. Let me check the sample. 50 by 50. So let's make this 60 by 60. Okay. So now for each of our cells, we need to read in our input. Let's call this k. So you would read k. Okay. So basically, you can see that. I'll actually put it over here. So here we go. Oops. Okay. Okay, so 1 means that there is a wall to the west, 2 means that there is a wall to the north, 4 means that there is a wall to the east, and 8 means that there is a wall to the south. Let's actually make this corresponding to this. We have W, we have north, we have east, and we have south. So notice that this is 2 to the 0, this is 2 to the 1, this is 2 to the 2, and this is 2 to the 3. So we can basically use our bits operator to find this. So it can be from 0 to 3, so it can do for int, let's call this big I, from 0. It can be less than 4. Okay, so if 2 to the ith power, if has any common digits with your k, then your g of ij of big I would be equal to 1, because it means that there is a wall. So that's basically there. So now we need to first find the number of rooms. So again, we would loop through our information, and we should actually, so let's have a basically, or we can actually define, or using, so this will make it simpler, and we can define a first and a second. Okay, so we should have because we should have it basically the corresponding to the parent, or the parent of the cell. So we can have a pi of p, which means parents. Okay, and then originally everything would be equal to, let's just say, -1. So now we need to start from here. We can start from any possible room. And then basically, if we already traversed this cell, then we don't need to do it again. So if g of I of j, basically dot p, this actually should be dot w, dot p, if it's not equal to -1, then you can continue. Otherwise, let's call this our depth first search. So we DFS from ij. So let's actually make this, yeah, sure, ij, and your starting node is ij as well. Okay. Let's make our DFS function. So it should be void DFS. So basically, let's just call this current and parent. Okay. So then you need to set the parent as that. So then g of c dot first, c dot second, dot parent will be equal to p. Okay, and now actually we should make our sizes. So let's have another like integer called size. Let's call this s. Or actually call this sc. So then the beginning g of c dot first, c dot second would be equal, or dot size would be equal to 1, since you have yourself as the size. And okay, so now we need to basically traverse into like all 4 possible directions. So you can, let's actually have our x directions. It can be 1, 0, -1, 0. Y will be equal to 0, 0, 1, 0, -1. Okay, so over here, because there's 4 possible directions, you loop through each 4 of those. Okay, so your new point would be, let's just call this actually a. This would be equal to c dot first plus x of k, and the c dot second plus y of k. So now we need to first check if it's valid. Let's make a function. So this should take in a pair. We have to return. Okay, so x dot first has to be has to be in the range. So here, and so this the column as well. Okay. So basically, if it's not valid, if A is not valid, then you can continue. Or if it's not taken, so if G of this, so you can do it over here as well. So if G of A dot first, A dot second dot P, if it's already taken, then you can continue as well. Otherwise, you just DFS A, and then the parent would be C, or actually P. Okay, so let's actually return the size. So if this returns the size, then since basically you're merging these two, then CF first, CF second would be incrementing by this. Okay. So now you just need to return your size. So G C dot first, C dot second dot size. Okay. So now basically the number of rooms, let's call this int num. Or int num. Originally it would be equal to 0. And let's call this our max size. It would also be 0. So every time we try to traverse into a new room, our num would increment. And then you can notice that your max since basically this returns the size of your component, your max size should be equal to max size, and this. Okay. So now not only did we find the number of rooms, we also found the max room size. Okay, so now we need to find the longest or the largest room. So max size from removing one wall. Okay. Okay, so again, we need to loop through all points. Okay. So we can loop through all 4 possible directions as well. So we can do for int k, or we can actually use the code from above while modifying it. Okay. So your new one would be I plus x of k and j of this. So if it's not valid, then you just don't do it. And then, basically, let's call this max size 2. Okay. So this has no meaning. Okay, so basically, if the parent of ij and the parent of a is the same, then means that you do not add these 2 times. So then, basically, or this should be our result, it would be at least, okay, let's actually make this simpler. Okay. It would be the size of this component. So then this would be, let me check, so g of ij dot size. But notice that you want the, basically the parent of this. So then this would be dot p. Let's call this int, actually pix. It would be equal to the parent of this. So it would be equal to g of x dot first, x dot second, dot size. And if x is not equal to g of, let's actually make this, let's call this y. So piy will be equal to the parent of a. So if the parents are not different, then you can basically add the size of y dot first, y dot second as well. So now you have the maximum size by removing one wall. So now you need to find which wall. Okay. So basically we can call this, let's call this wall. And you can call, or actually we can find this above here. Okay, so notice that we want the leftmost point. So it can only be either going east or it can be going south. Or yeah, it can be either going east or south. So then, example you can see, or actually can be either going north or east. So then, you can loop through only the k from 1 to 3, or 1 to 2. Okay. So now you know that basically you know the size of this shape. Okay, so first, since you want the what do you call it? Okay, so you want the most, 1 second, let me check this. Okay, so you want to first choosing the most west one, and then you want the most south one. So then, to do that, you can do, okay, to find the most west one, you would start from the columns here. Now you can actually just change the order. And now you want the most south one. So then, since the more south, you have to go more down, so then you would start off from n. Okay. So now basically we need, oh yeah, I didn't update the max size. So basically if res is greater than the max size, then your res will be equal to the max size. Actually, max size will be equal to res. And then you would update your answer for the wall as well. So let's call this PI answer, or actually wall. And then you can also, let's call this the direction, so in D. So then your D will be equal to K, and your wall will be equal to IJ. So let's actually print. So now we need to basically write answer. So first we need to print our number of cells. So print num. So now we also need to print the maximum room size. So max size. Next we need to print the maximum size 2. So CL max size 2. And then we need to print our wall. So print wall dot first, wall dot second, and then you need to print the direction. So it would be dir of D. Okay, so this is usaco-training, and this is the castle. Okay, so let me run this. So run main. Let me take the input. Okay, it's compiling. Whoops, okay. G, so unexpected token. Let me see. Okay, so maybe this isn't like a valid like constructor. So you could do this 0, 0, 0, 0. It's compiling again. Oops. Okay, so apparently I can't do this type of like conversion. Okay, so line 32, you can check over here. So if g of a dot first, a dot second dot parent is not equal to negative 1. Okay, so I would say that this did use the like type definition. Or we can actually make this called PI, because there is a constructor. We can also do it down here as well. Okay, that should fix it. Okay, let me give the input. So we got 22, 28, 28, 71, which is not what we want. Okay, so we can actually try to see this. Okay, so pi of that. Each cell has its own like unique thing. So we can actually print which cells and which parent. So we can see out C dot first, C dot second, and this would basically be from P dot first, P dot second. Okay, again we can run this. Okay. So a lot of these are from 1, 1. And then you have these rooms. Okay. So then you can basically, so you have your max size, or we can actually just see out IJ. So we can know that this is the parent of everything. Okay, so we actually have quite a few parents. So you have 1, 1, which is a parent which is correct, and you also have 1, 5, which is a parent which shouldn't be right, since the next note that should be processed should be 1, 3. So that should be something wrong with here. So wall to the west, north, east, and south. Or we can actually do this instead. Okay, so basically you can start subtracting 8 first. So if k is greater than or equal to 8, you would subtract 8, and your wall of, here we have 3, will be equal to 1. Okay, now if k is greater than or equal to 4, then you would subtract 4, and gij dot wall 2 will be equal to 1. Now if k is greater than or equal to 2, you can subtract 2, and then gi dot weight of 1 will be equal to 1. Now the last case is if k is equal to 1, then you subtract 1, and gij of weight 0 would be equal to 1. Okay, now you can, whoops, I meant to mark that out. Here we go. Again, we're getting the same answer, which means that here is not the problem. So we can actually just add another like Boolean value, which means if it's visited or not. So originally it would be equal to false. Okay, so basically you want this, so if it's not visited, if not dot visited, then every time you just set this as visited, dot visited would be equal to true. And down here, basically you would say if it's not visited, so if not visited. Okay, so now we actually should remove the CL. Wonder where that is. Oh yeah, that's actually from there, so let's actually run it again. Okay, it's still compiling. Ooh, okay, so we're getting none. Okay, so maybe there is some kind of like definition issue, so let's just do gij dot visited equal to false. Gij dot, what do we have? We have parent would be equal to -1, and gij dot issue dot w would be equal to via vector bool 4. Whoops, that shouldn't be doing that. Okay, let me get the input again. Okay, so again we're getting nothing. We can actually print out like which parents we're getting. So if not visited, oh, basically there should be if it's visited, then you don't do it. So I actually messed it up. So again, if it's visited, then you don't do it. So let me actually remove this mark. Okay. Okay, so 22, 28, 28. That seems like incorrect. So if there is a wall. Oh yeah, so I forgot to check if there's a wall or not. Oh yeah, and I also messed up N and K. So this, I should actually read it in terms of M and N. Okay. So I actually did not mention the wall at all. Okay. So as you can see, when we're moving from one node to another, we have to make sure that there is not a wall. Okay, so we should actually reorder this. So you can see, first one is W. So W means that it's going west. So the y coordinate should be shifting left, should be going -1. This would be 0. Second one is north. X would be moving -1. Here we have east. So there should be 1, 0, and the last one is 0, 1, 0. Okay, so over here, basically, if there's a wall, then we don't do it. So if G, A dot, or C dot first, actually, the wall of K, then you continue this. Okay, it's compiling. Okay, it's running. 3, 9, 16. Okay, so 3 is wrong, 9 is right, 16 is also right. So at least we got some more cases. So let's actually just print out all our, like, oh, there should actually be sorry about that. Okay, it's compiling. 5, 9, 16, 4, 1E. So nice, that's what we want. And since we're actually reading and writing from file, I'm just going to use freeopen. So freeopen castle.in using reading stdin freeopen castle.out write std out. Okay, so let me just submit this to make sure. So my ID is DOM3. This problem is castle, and the language and C++11. Okay, so okay, here we go over here. Okay, so let me select my file. Okay, this is usaco-training, and this is the castle. Okay, here we go. Okay, so it says that. Okay, so so there should actually not be a character. There should be a string. 1 second. Let me just change this up. Okay, let me submit it again. Okay, so it looks like that is right. So if you have any questions, feel free to leave them in the comment section below. Bye.